All right. It's my pleasure to talk a little bit about the work I did over the past 20 years or so, both while professor at the university and later in industry, on the subject of graphs and knowledge representations and so-called network science, and how I began to use ArangoDB as a key tool in that work. I'm going to try to explain the method for modeling data that came out of many years of trial and error. And it's perhaps a surprising idea, namely that the basic properties of space and time are in fact at the root of almost everything we do in information technology. We can organize our thinking about information, analytics, data, by thinking about space and time. And we can view space and time themselves as being programmable, as a way to understand the complex network of services and interactions in the world around us, from biology to modern living. Now, usually if someone talks about space and time, we probably think of Einstein, but that's not what I'm talking about here. Space is just the name that we give to a set of real or virtual locations at which we register information, write documents, and time is just a counting sequence of changes at those locations. This is called the proper time. And this is true in Einstein's picture as well, although I'm not going to try to explain that here. We can maybe leave that for questions at the end if anyone is interested. Well, it's a subtle idea, but it's not a difficult one, and I've written books and papers about this in the past, as well as a series of blog posts recently called Data Analytics and Semantic Spacetime. So I'm going to summarize a little of that story here today. Here's the plan. It forms a little semantic space-time of its own, a storyline, a chain of reason. I will begin by telling you a little bit of context about the method and how it can be applied in programming. And I want to focus on an example because I think examples help to bring out some of these issues more clearly. And I'm going to use Traceroute, Internet Traceroute, as an example to build a graph from one graph, the Internet, to a graph in ArangoDB. And then we'll identify a principle around space-time thinking called the coincidence principle, which allows us to model in a clean and separable way, in a way that will lead to predictions. And it's based on four simple ideas, four classes of edge in a graph: containment, following, expression, and similarity. And finally, I'll discuss a little bit of the applications of these ideas, specifically to edge computing. So, if you are sitting comfortably, I shall begin. For those of you who don't know me, I started life in theoretical physics, quantum fields, all that, and then moved into computer science during the 90s, creating the precursor of what we now call cloud computing, and looking at models of how to understand computers as a behavioral system, not as a programming system, because what we intend computers to do is one thing. What they really do is perhaps something else. So, as a phenomenon, perhaps more like David Attenborough than Frank Lloyd Wright, and understanding computers informed by the programming, but not determined completely by it. And this led to a study of processes in general, fairly abstract thing. Sometimes we use processes in control systems, say in cybernetics. Other times we're just trying to understand the design of something. And graphs appear in all of these cases, quite importantly. So in this image, the layers of infrastructure on the right-hand side each contain graphs representing many different levels, a little bit like the OC network model, multi-layers of the network. Or you could say even different scales, or time scales. And these all contain processes that contain patterns. And when collecting and analyzing data from systems like this, we need to trace not only the values that are changing, but also the context of those signals in order to give them meaning. And we use data analysis for this in two different ways. There is the scientific tradition of placing all of our trust in data as a source of truth, and extracting patterns from the data under controlled and repeatable conditions. Then we use statistics to extract invariant properties, properties that don't depend on a particular experiment, but will be found again and again by repetition. This is what we mean when using data for understanding. But then today we also use data in another way, which is to paint pictures, essentially, combining multiple sources of data from different circumstances, different experiments, to create a photo-fit outcome, like a customized service, or a more beautiful face, or a better chess player. And this is the idea behind AI. Then the goal is not truth, but something else, a kind of painting, some kind of constraints on the output, like an error function will decide the criterion for what is a good outcome or a bad outcome. But it wasn't an outcome that was originally present in the data. It was a merger of those things. There's a creative element. And this is engineering. So there's understanding and engineering. And my journey with graphs and data began in these early 90s when I built some software called CF Engine, which was something between a cybernetic control system and a cognitive learning process, gathering data about machines and how they were functioning. CF Engine was a collection of autonomous agents at the edge, if you like, of the network, a so-called distributed system or an ecosystem of independent software entities, each agent acting on its own, but able to share data and communicate with others, forming a dynamic graph. This is what we call a graph cellular automaton in academia. As a model designed to reach a stable outcome, CF Engine was called a desired state outcome. And it was an approach that was closely related to these graph computations that we see today, like Google's Pragle system or the Apache Giraffe, where the nodes in a graph act almost independently to form a computation by communicating with neighbors, message passing. And this is very interestingly being built into ArangoDB today. Now, excuse me, in this picture, graphs appear all over the place. For example, there is the Spacetime graph of infrastructure and events on these lower layers, and another Spacetime associated with concepts, the knowledge space of concepts and the stories about the system. And we developed and sewed these different graphs together to form a map of the documentation in the system, and a dynamical map of the state combined with the knowledge about the documentation. And the usefulness of these graphs as process drivers as well as process snapshots was really on display in these early adventures and motivated me to develop some of these ideas. And I mentioned the CF Engine because it used data stores in every possible way, at the edge, inside the agents, and then centrally aggregating the data from agents to build an overview of the dynamical state and sew that together with the documentation. Now, CF Engine used machine learning in the scientific way to accumulate and find patterns. And the left-hand side of this picture is from CF Engine. You see how it reveals from the statistics of connections to the system for the first time that there were patterns to process behavior on different timescales, even across something as apparently random as clients from the internet. And these patterns could be captured using key structures in the learning databases to build up periodic patterns like this, mapping regular attributes in time to key values like, say, Monday, Tuesday, Wednesday, these peaks. In order to form in order to transform a potentially infinite stream of events into a reduced dimension pattern or structure that we can learn from and predict from. And so CF Engine's machine learning was not the kind of massive deep learning that grabs the headlines today, but something closer to the kind of inexpensive learning that you see on a basic level in biology, the strengthening of a muscle by exercise, or the setting of a bone in response to external stresses. Now, somewhere in the middle of that story, I also got involved with telecom researchers here in Norway to study large networks like the World Wide Web for security and strategic planning, extending the PageRank idea that Google came up with to importance ranking and search possibilities in directed graphs, not just undirected ones. Anyway, as time went by, I wanted to tie all these ideas together and the techniques and apply them to the problem of knowledge management, reasoning, diagnostics, discovery, to build smart and expert systems that could explain data by chaining them together in meaningful ways. Because it turns out that it's easier to grow a system than it is to understand one. We can build these systems, these huge systems today, but to understand them is really quite hard. But the physicist in me felt we ought to understand them too. So long story short, this eventually turned into a project called Semantic Spacetime, which I've been blogging about in this series recently, and been using ArangoDB to implement the examples. The techniques we developed also over the years are still waiting to be applied today. We're very far from being at the end of this story, and particularly in the area of data pipelines, because data is so prevalent these days. The world is a gigantic data pipeline from top to bottom, or from bottom to top, I should say. Well, one of the things that came out of that work was something called promise theory, which is in fact a detailed algebra of the connections in a graph. And I'm not going to talk about that today, but I do want to talk about something that came out of promise theory, which helped to solve the problems with knowledge representations, especially in taxonomy and ontology, where systems like topic maps and RDF, OWL, the semantic web, and so on had all tried and failed in the past because they were too restrictive. Links or edges are more like Shannon information channels than Cupid's arrows, formed by overlapping alphabets or pointy Venn diagrams like lock and key fits. And this is how semantic spacetime views connectivity in a network. But in other words, to give a full description of the world around us, what's possible and what can happen in every place and time, at every level of description, we can view the world as a set of location-embedded properties around agents or nodes in a graph, functional services that are connected together through a network of interactions, lock and key fit, and the changing configurations of that graph over time, just like CF Engine Cloud configuration, also like artificial biosystems. This is the idea in biology and neuroscience as well. So the idea of processes as webs of interaction became really important. Okay, so one version of this story begins with a simple insight, which is that graphs are a better representation of processes than we're generally taught in schools. The Newtonian way of thinking about change that we're taught in school in terms of things and objects that move around in some empty space, where space is measured out as a kind of theatrical stage on which events take place. That model isn't always appropriate for understanding systems. Because, what do the spaces in between mean? The Euclidean Minkowski space that we use, where we have coordinates for everything, isn't a good fit for everything, even though we're sort of stuck with them because we're taught them. And machine learning falls back on these embeddings of graphs into Euclidean spaces today for that reason, because it's sort of familiar, it feels good. But graphs are generally more efficient because they model only the salient points and only the direct relationships between things. And all of that sort of speculative space in between can be eliminated to give a simple skeleton of the system. So if we think like a database for a moment, the names of the keys that we use for storing and retrieving data aren't always independent random things that we just want to number with some coordinates. In modern usage, especially in technology and services, they may actually be ordered storylines, delivery chains, logistic chains, chains of dependent events, streams, things that form networks within networks, where embedded document data can be found at each location, even moving along the process chain. Lock and key offered and accepted. This is why graphs are key in modeling, no pun intended. And this is how, for me, the Arango model became a simple tool where a bunch of other databases had failed. And I could give up writing my own tools finally. The model is sort of just what we need for our present day understanding of science and governance in technology. Because we don't want to create these sort of dead graveyards for data to lay down and rest, giant archives like you find in the tax office, with the occasional SQL exhumation of a body for analysis. But rather we want to study these living systems where we're interacting and moving with the system, flowing along lines of change, streams, where we keep our hands in the picture, interacting with live data as an ongoing investigation, a bit like a murder inquiry. And the role of time between source and observer is an important driver and key here as well. So, well, to get a feel for the problem, let's start by looking at an example of this. And let's examine the internet as a graph by doing a traceroute probe of packet delivery and try to model that as a graph. And then I'll come back and look at the picture, the bigger picture with a taste for the context later. And let's start by running a raw traceroute first, and then use a program to capture and analyze that output. So here's one that I made earlier, as they say in the cooking shows. Okay. Now Traceroute works by sending out probes of increasing range. And each time these packets hit something that looks like a router with a different IP address, they get echoed back. So we get to see the different stages and map out the routes taken from here to there. It actually sends out 3 sets of packets with increasing range, so that we should get an echo reply from each leg of the journey. We may get 3 replies from one location or a reply from 3 different locations. And because, like a good statistician, it knows that the actual path might be changing on a real-time basis, it tries to accumulate these 3 packets and figure out whether there's variation, whether it's repetition. So routing is not a static map, it's a real-time process because there's a rolling traffic picture that we have to adapt to. So here you see addresses, you also see CPU clock times and sender waited for return. And there are stars here as well. These are not the result of hitting our head on the router too hard. Traceroute is the merest kiss of a router awaiting a harassment lawsuit. But these stars actually tell us that the router wanted to be anonymous. It refused to return its IP address. So we don't know exactly where it is or who it is. Now, if we look at this schematically, it looks like a branching process, spreading out and then coming back together, depending on the space of possibilities that are uncovered. So this is the general kind of topology uncovered by this process. Serialism and parallelism ongoing at the same time. Okay, so now we can parse this with some kind of code. And you'll find this in the GitHub repository. To begin with, we simply suck up the output from Traceroute, form a pipe, and then we basically use a memory process to join up the events as nodes or vertices in a graph, connecting the previous node. So we remember the previous place we were, and then each new event we connect that previous one to the current one to form an ongoing chain. And notice we use these derivative functions, create node, create link, and so on, which are based on the Arango API. You'd never recommend someone to use the raw API unless they were doing systems programming. When you're modeling something, you always want to create your own layer for ease of understanding. So we run this, and if we look inside Arango now, we see the library code has generated a bunch of generic collections, far more than we need actually, because the generic code is suitable for a wide range of models. We're only going to use two of them, nodes and hubs, and follows and contains edges, which I'll explain in just a minute. But if you were tailoring your own application, you might want to slim this down a bit, but this generic code is sort of handy to use. There's a price for it being generic, of course. Now, the first question we face in capturing a process of events as a graph is, how shall we name the nodes? They need to be distinguished, they need a key. Here it's an easy choice because the process is just an arrival at a location. And luckily somebody has already solved that for us by giving IP addresses to the nodes. We could also use the Ethernet addresses, of course, the MAC addresses. They're also unique. Every network interface has an IP address. Here just the IPv4 addresses. And so we connect the graph by remembering the previously visited node and joining it to the current one. And if there are several, we connect them all in parallel. Then another issue arises if there are three or more alternatives for a leg of the journey, which all play the same role. What do we do about that? How do we keep track of this grouping of alternatives that play the same role? And one thing we can do is to create a hub. We can join them together by drawing a ring around them, essentially. And we draw a ring around them by connecting them to another kind of node called a hub. So it becomes a kind of bipartite graph. And then we keep those in a different collection. What are these hubs? Well, we ask ourselves, what are the semantics of these alternative paths? Do they indicate nodes that belong to the same subnet, perhaps? Or do they belong to the same organization? Are they a group of organizations? Are they an internet exchange? You know, we can't really tell from the information from Traceroute alone, but later we might be able to discover the identity of these things or the reason for this alternative nature. Well, whatever they are, we can model them as a different collection in Arango because they play a different role to the ordinary nodes, the raw nodes. And by that I mean that the documents that describe them will play a different role in the model. You might think, as you might do in SQL or in a database like SNMP, MIBS, or Common Information Model, you might think that the right thing to do is to separate collections by manufacturer of the node, like Cisco, Juniper, Dell, IBM, something like that. That would be a SQL approach of typing. But they all play the same role, so we don't really need to separate that. We can just label them as different kinds of components. But rather when they play a different role, like an organizational entity, which doesn't affect the process itself, but it's kind of an observation, then we can separate that because it's an entirely different thing with different data, different kind of space. So what we see from this example is that a route is not just a single collection of points or locations connected together in a chain. It's a series of events in a process storyline that could occur at one or more several possible locations. Right? An event, even an aggregate event over multiple runs of the experiment, has a symbolic role which is different from the actual location. So there are two kinds of space going on here. There's a detailed view of location, and then there's a virtual view of location, which is the role played by the process. And if we repeat this experiment multiple times, these things accumulate over time and form larger groups. And sometimes a hop in a link might diverge, like going through multiple slits in quantum mechanics, and sometimes they converge and come back together. Now, this is a good point to mention another great space-time principle. So I should have perhaps said that, aggregation is a form of space, and the sequential hops are a form of time in this process. But so these are space-time principles. And another space-time principle that we use to model is called the coincidence principle. Let me try to explain it with a slightly more complicated example, just very quickly. Because this is the basis of learning in neuroscience and bioinformatics and natural language programming, all of these things. The general principle for building process graphs, and therefore space-time graphs, is to use coincidences in space and time. And I don't mean coincidence in the colloquial sense of a surprise. That was surprising, what a coincidence. I mean the arrival of things together at the same point. And whenever things come together, they form connections, or we can connect them together because that's an indication that something happened between them. So even in this simple traceroute case, a lot of issues pop up. But the good news is that these are universal issues, and we learn them once and we can reuse them over and over again. But in a more complicated series of trajectories, going back to the CF engine example, lots of ongoing processes, not just a single trace route thing, but independent processes interacting on humans scales as well, with machines interacting with humans, humans interacting with humans, machines interacting with machines. All of these form a web of interaction. But suppose you have a process where somebody is moving around different countries in the world and visiting different countries with passports and different documents. There are all kinds of things to model like a graph here as well. And in this little snippet of code, we may want to create the objects, the documentary evidence, the documents surrounding particular entities like countries and towns, so France or Paris. So we create functions for that to register in a database. And then we want to connect some of these things together to express relationships between them. For example, Paris and France. Paris is a part of France, but we can view this as a coincidence of Paris and France. When those things belong together, they belong together according to the relation part of. Part of is a spatial relationship. If I am inside the boundary of France, then I part of France. And then other kinds of coincidence, some of them are sort of sequential events, like a country issues a passport, happens at a certain time, certain date, and then lasts for a certain time. Country issued a visa, allows somebody in. A person arrives at a location, Mark arrives in New York, Emily arrives in Paris. These are events, they bind together other things which are invariants of the process in a temporal transactional thing. So we have two kinds of events, two kinds of object in a process graph. One is an event, which is just an ephemeral historical thing, and the others are long-lasting, persistent, invariant things like people, things, keys, visas, and so on. So we register documents, we register events using these coincidence functions. And it doesn't matter how many times we repeat the registration of these things, as long as we make them idempotent and convergent. Doesn't matter how many times we repair them, because they're invariant, we won't change them, and therefore we have a safety net on registering information. Now, in neuroscience, they have this great expression which captures this principle, which is that neurons that fire together wire together. And it's the basis of all learning in graphs, that whenever two things happen together, whenever two sources come together and interact, they form a link in the graph which documents that connection between them. And that is learning. The placement of that link is a form of learning. Now I focused on the structure of the keys and ignored the values in the database, partly because Traceroute doesn't tell us anything about the locations. But a graph database is only a graph in the keys. The values are just like any other database. It's just a document, something like JSON document in ArangoDB, very nice. But we shouldn't also forget that a good graph database also should contain these values. One of the themes of space-time, whether we're talking about real or virtual space, is coordinates. And coordinates are just the names and addresses of things. So names play a role not only as a key for looking up some information, like in random access, but also as the first expression of what makes it special, right? Its semantics. So we try to give meaningful names to things that are different when the difference between them is important. And if the difference is not important, then perhaps we just number things to say that there are equivalent cases or instances of the same thing. But we still need to name things in creating objects and entities in our space. And actually, we only really care about naming these invariant things, the things that don't change during different enactments of the process. And we name invariants because the real key to data is the context that led to the data, the circumstances that we want to characterize. And that leads to this notion of reinforcement learning as we encounter the same things over and over again and link them together, perhaps the same thing multiple times. Each time we link the same things together, they become a bit stronger, like strengthening that muscle, like setting that bone. We form that skeleton because of the invariant nature of the things. And I want to make a brief aside here because there's a really important point which I've seen, it's a mistake I've seen in certain books on graph modeling. The nameable objects should be invariants. So we don't want to say something like a person emails another person in a graph database because it's ambiguous. What does that mean? Do we mean a single event in which Mark emails Sarah? Or do we mean the ongoing state of having once emailed someone? Mark emailed Sarah once and therefore they know each other. These have very different semantics, an event versus an invariant. And trying to represent invariants by links like this is clumsy, and this is the mistake that RDF makes. It makes it very difficult to reason about things. The way you want to model events is as nodes, which then refer to invariants by a different kind of link, this containment kind of link, which we use to form hubs. Now, when we do that, we can do something nice, which is prediction becomes very easy. When we wire together graphs based on repeated evidence from these streams, we can encode sequence by linked up events, and we can encode membership by using membership links. So time-like links for event propagation and space-like links for membership location. And this is where the space-time insight comes into play. No matter what kind of scenario we imagine, it turns out that the edges of processes always fall into one of four possible classes. And here they are. I call them contains, like being a part of something, follows, that something comes after something else, that something expresses information, like a document contains members, so sharing information with other nodes potentially. And then also the notion, the equivalent of distance in a graph is the notion of similarity between nodes. Are things wired together and connected together because they are somewhat similar to one another? So with space-time edges in a causally mapped graph, we use follows links to find future outcomes. We want to go forward in time from a given starting point, but we can also go forward in the sense of generalization by seeing, are we part of a larger structure? So an instance of a larger structure is part of that structure, and therefore a contains link allows us to go up a level of generalization. And prediction now becomes trivial because we captured causality and we separated it from other relations like containment or generalization of concepts or of space, of localization. You know, Paris is part of France. That's a generalization of Paris to France. And this leads to a huge simplification and separability of the algorithms. We might not actually know the precise name of a relationship following connecting things together like A emailed B. But if it's causal, then we can simply examine follows links or contains links. And we generate stories to create this structure, which we call the cone of semantic future. In other words, all the nodes that we can reach by following these causally transitive nodes from where we are currently. Not the cone of Christmas past, but something more like the light cone of semantic future in relativity. So this all comes out of labeling the edges using these 4 space-time patterns. Can it really be true that there are only 4 classes of edge? Well, of course, we still need the detailed labels to say precisely what going forward or coming after means, but yes, there are basically only 4 types, and it's not hard to see how that would arise. You know, back in the primordial soup, where our senses evolved and our notion of concepts evolved before we'd invented fashion and Coca-Cola, you know, there was no dictionary or encyclopedia of concepts to imagine. There was no shelf of products to choose from. The formation of ideas and concepts could only be based on what could be sensed in the space around us over time. There was no red, green, blue. There were no cars, houses, only up, down, left, right, before, after, inside or outside. So senses could evolve only to discriminate those basic distinctions, and therefore it's natural that all concepts on some level are aggregations of those. Now in object-oriented programming, which is quite familiar to many, we use encapsulation, which is a contains relation, almost exclusively to try to model data. This has a lot of problems, and OO modeling gets into serious trouble in the same way that, or in a similar way that RDF gets into trouble. And it kind of leads to the type model, the SQL model, the relational model, the schema model. You can't model time easily in a schema model. So we end up having to generate lots of other kinds of database, like time series databases, logs, journals, and things like this to capture data, and then trying to convert from one to another, and then using Elasticsearch to find relations and so on. It's all a big mess. But in a graph database, you can do all of this at the same time. Well, what's it useful for? The short answer, of course, is everything. There are these sensory loops on all levels in the world around us, these cognitive learning loops where we wire together things that appear together, or co-activation. This all began, like for me, with the desire to manage systems and describe systems at scale using CF Engine or whatever. But now just imagine the world of edge computing, of smart spaces, houses, cities, the dreams of 5G that we've all been told about. No matter where we're talking about processes of user interaction, there's pattern recognition, flowing rivers of data, change, climate models, motion of trains, planes, automobiles, sensors passing data along pipelines to the internet, aggregating them, piecing data together to form maps and models, solving mysteries like CSI, forensic investigations, and so on. All of this is a giant storytelling process that graphs are very good at doing. And we're really just talking about the careful labeling of events in space and time, and then figuring out how to connect them and parse them to make predictions, which is a very long way from the story of random access retrieval that we have in database thinking of yonder year, of the past. Well, We've hardly begun, but I kind of need to wrap up here. I think there's a lot to digest already and the time is passing. I've tried to tell you this storyline, this graph that I described at the beginning, to illustrate how simple, universal ideas about space and time, containment, order, attributes, similarity, how these ideas basically govern a chemistry of processes between invariant things that form graphs whose structure allows us to make predictions. 4 types of edge: containment, sequence, expression, similarity. The point of semantic space-time modeling is that it allows us to stay in control of reasoning by reducing to these 4 types, these 4 basic vectors. Sometimes people assume that the point of graphs is to be a visual representation because they make pretty pictures. But at scale, when we get very big, the structure or layout starts to become very, very hard to see, quite inscrutable actually. So the ability to visualize becomes less and less useful. Just look at pictures of proteins if you ever want to see that. The point of graphs is not to make nice pictures at scale, but it's to ensure that the detailed links, the bonds in between things can clearly be parsed with the assistance of machines. Sometimes people cheat. They try to resort to embedding graphs in a Euclidean space and then using ideas like distance, which are very easy to understand. We do it in principal component analysis, centrality, and so on. And this is being used a lot in machine learning now as a certain approach, this Stanford approach, I suppose you could say, to dealing with some learning processes rather than using directly in graphical form. And I think this is not a good idea. I believe they probably did that because the tools for parsing graphs were not really available before. But as I've shown in my blogs, Arango has come quite far in enabling such tools, and there's still plenty of room to develop that, which I hope will continue to work on. So embedding, the problem is we may fundamentally change the information by adding points that weren't there. It's very speculative. And these distance functions, although easy to understand, easy to visualize, might be somewhat simplistic. They might not capture all of the nuances in all of the detailed document semantics. And then we end up having to regularize, renormalize, eliminate infinities, and dimensionally reduce again. And the result is, we may throw away a lot of information. So, finally, what about Arango's role in this? The ability to attach semantics to keys of different kinds is the key to modeling. SQL-like languages are designed for random access searches. And a lot of SQL-like languages, even in some graph databases I've seen, are basically for random access usage, where you store things perhaps in self-similar archives, type models, static snapshots of reality. So it's that dead data archive like they have at the tax office. But in AQL, we've designed something for interactive process discovery in causally ordered, dynamical flow spaces of possibility. Very grand. It's a much more dynamical picture, and it's much more like the real world. What I like about Arango is that it's been designed in a practical, process-oriented way. It doesn't force you into a badly fitting shoe. It lets you model in a way that fits each process individually. And its superpower is kind of this flexibility in choosing the type of key to fit the role in the process that we're trying to model. Process modeling is about finding the right coordinates, the names, the keys, the invariant facts, which are persistent knowledge, separating them from the transactional events that tell the stories, and doing it in a way that allows us to understand the difference between what is temporary and what is permanent. So the river is never the same twice, but it's always cold and wet. So let me stop here. I hope you enjoyed thinking through these issues, or at least I hope that it will help you to make better choices when using some of the features in Arango. It certainly helped me, and I hope you'll find that the blog series, which is much more detailed, will be a useful reading list. All of the code examples are there in Go, a very nice language for using together with Arango. So with that, Godspeed. Let us celebrate the incredible circuitry of the world and all of its glorious graphs in these Arango days and beyond. And do enjoy the rest of this event, and I hope these points you can take home with you to give you a more successful experience around using Arango.